Hello everyone. Good morning, good afternoon, good evening for someone. I'm very happy to see you today on the live event here on LinkedIn about the demystifying or decoding compressed air. We'll start right now. And I'm very happy to see that more than 130 people subscribe to this. And for those who cannot join now or cannot follow the full webinar today, for sure we will have also the recording. And as now today in Europe 2:01, I would like to start. So if there are any problems, you cannot hear me or anything, just I have my chat here open. So I already see Olivier. Hello, Olivier. Bonjour. Familiar faces. Here, my colleagues and people with whom I used to work, people that are work now, people that are passionate about compressed air. And today I offer you, let's say, a fun, relaxing 1 hour, 40 minutes on the decoding compressed air or demystifying compressed air. So I chose it on purpose, this topic, and because I've been working in compressed air for 12 years and I come from the research background. So I studied, I did my master's, and I did even PhD on this. So I spent some years on the lab, uh, checking the test rigs and understanding how the system works. And I always had few questions, and my all questions were why it has to be like this. So why there are some best practices, as we call, or why manufacturer did this, and why it's still like that, and what is the technical reason for this. And the same thing happened when I started to work in the industry and I started to help customers to optimize their systems. And they started to ask me, Elvira, why it is like this? So why we have this technology here? Why we work on this pressure level here? It was supplied like this. So let's talk today about this, and very welcome to have your comments and your feedbacks here. And as I said, just fun, interesting information. Maybe you already know, maybe you didn't know about it, and maybe you can discover something more interesting about compressed air. So I would like to start with a thing that calls magic numbers. We know, and especially people that work with this domain very close as an energy manager, and you have your facility, you know that 6.3 bar system, it's a very standard pressure level system, right? So we need to have 6.3 bar, either the compressor or the component better. Then we have a certain pressure drop, and all the system run at 7 bar. This is the optimal pressure level. Then we have some magic numbers on the component sizing. So if we take the standard ISO cylinders, actuators, we have a tables, everything is standardized. And it is wonderful that it's standardized because we can replace various components, we can work with various suppliers. However, there are still some magic numbers there. And another magic number, and one is of my favorites, the pressure drop within the application. From half a bar, 0.6 bar to 1 bar, it's considered to be a normal pressure drop. This is for us nowadays the state of the art. And we all work with these pressure drops. We work with the 6.3 bar at the application, as well as we work with the certain components sizing. And let's see, is it actually true? And what is the technical sense behind it? So just for you to refresh a little bit the basic of compressed air. So compressed air, when we talk about, for example, 6 bar of compressed air, it means that we take one volume of the 1 cubic meter and we put there 6 times 6 cubic meters. So this is 6 bar compressed air. So we always work there with volumes and we always work there with the pressure. And why this magic number matters, why this 6 bar matters, why the sizing of components matters, or pressure drop, because this actually creates, and this is the part of the energy consumption or your energy bill that you pay, and also system performance. So our energy consumption depends on the pressure level that we supply to the system, plus the pressure drops that we need to that occur there in the system, even if we have a perfect system, times fill-in volume. Fill-in volumes is all the volumes that we need to fill. So it's the geometry is the of the cylinder, for example. It's all the dead volumes that we have. It's the flow in application where we need the flows. It's all the tubing and so on. So this is basically our system performance. We always work with pressure and with the fill-in volumes. Since we consider we don't work with the temperatures there and we have a standard temperature, we likely ignore this factor in our consideration, in our energy consumption consideration. However, it has some impact, but not a big one. So, and the first magic number today I would like to discuss with you and unveil is the pressure level of the system, 6.3 bar. I put here a magic ball for a reason, because I was always asking actually why it is 6.3 bar. While I was working in the lab, and every time I turned the pressure regulator to the 6.3 bar, I was waiting for something. Something had to happen there, right? Because it's everywhere. It's written 6.3. It's not 6, it's not 7, it's not 6.5. There is something mysterious in the 6.3 bar. So how did we start, how I started my journey personally look for the technical explanation of this. So first of all, I did some questionnaire of the maintenance managers and also of the suppliers of the equipment, suppliers of the compressors, auditors, and everyone confirmed this is the best practice, this is our baseline, and this is the standard. So whenever the system would work under 7 or 8 bar, everyone would say, no, we need to reduce it to have 6.3 bar at machine. The next one question about the 6.3 bar, I asked the suppliers and auditors. So, and they also confirmed that this is the best practice and this is recommended by manufacturers. And the third one, of course, I checked with manufacturers and they confirmed the same. So I should have stopped here looking for explanation, but luckily I was invited to work as an expert in the standardization committee, and I started to talk with people. So where are those numbers coming from? And why it is 6.3 bar? And of course, you can go on Google nowadays and check this question. And if you Google 6.3 bar, and if you talk to the manufacturer of the pneumatic tools, like the drilling tools, so tools for assembling, they will all tell you that they work under the pressure of 6.3 bar. It is recommended. And it is recommended because of their torque that these tools provide. So basically, if you see here on the table, this is one of the manufacturers, you see in this table that time to make a hole and the maximum torque, for example, for assembling, it depends. So the mechanical properties of these tools, they depend on this. And they are designed for this pressure level. So once again, we have here the certain application for the of compressed air, just one, for the pneumatic tools, and they use 6.3 bar to perform it. And then they said, then you have pressure drops in the system, and maybe the compressor unit is 7 bar. So my question was then the next one again, why those systems actually were designed for 6.3 bar. So I'm waiting for the next slide to show you on the screen. Here it is. And here it's another interesting historical background. 6.3 bar, it's 90 psi, because we use the C system, right? And for example, in the US, we would use the 90 psi. 90 psi was chosen because it's a technically reasonable pressure that compressor could supply. Plus, it's a pretty number. So I've been told like this, it's a pretty number. And if you translate this pretty number into the bars, it's going to be 6.3 bar. And this 6.3 bar was adopted in all countries. Because this standard for those tools, it was first developed in the US, and then 9TPC was adopted there, and then I mean, agree, it's a nice number, right? Like 90, not too high, not too low. Very nice, pretty number. So, and also, moreover, they were adopted not only in the other countries, but they were adopted in the other industries. So it means that the pneumatic tools, only for few applications, this pressure level and the standard of the pressure and this explanation of this technical sense was also adopted in other industries. But pneumatic is, in compressed air, is more than just like drilling and checking all this like machine tools, right? We use pneumatics in food and beverage industry, in compressed air. We use in precise manufacturing, pharmaceuticals, automotive, pulp and paper, petrochemicals, cement industry, metal production, production of energy. I don't have, of course, all the applications here, but you probably also know better than me. We have also woodworking machines. We have various industries where we widely use compressed air, with not only used to fix holes with the pneumatic tools. And those applications of compressed air, they can be divided technically in the 4 types of the application. So the first type is, of course, the working air that we use in the automation. And for each application, we have then a certain equipment, right? So we have automation, we have the painting application for the explosive areas. So this is we call as the working air. And there we have a certain tools, certain equipment and components. We also use it as an active air for material transport and also for the bearings. In the process air, for example, in the cement, in the chemical industry, for drying, for the ventilation, for the fermentation, and we also use it in the vacuum. So we can use it as the ejectors, or we can use it as the vacuum pumps. So here we are actually beyond those drilling and assembling, right? So we're beyond those requirements or standards that were developed and adopted so many years ago. And if we actually go a little bit backwards and question ourselves, do we actually need 6.3 bar at all our application? Do we need this pressure level? Do we need pressure at all? Or maybe we need a high flow there? So those questions that I would like today to discuss with you and to show you and to show that there are standards way to optimize compressed air system nowadays. However, we need now to follow better practices, and we need to follow just a new thinking of the design of compressed air system, as well as more efficient technology. So let's think together. We have the application of 6.3 bar for assembling, but what if we follow the same logic and we go to all other applications that we have? And we see, do we actually need those pressure levels, or what we actually need for our compressed air system there? So let's go ahead and see how air is used beyond those applications. Today, I would like to focus just on a few applications. So this is mostly used in the working air. So basically the first type of the application that I showed you, and there, and also the vacuum. So, but today let's talk about the first step, the working air. In the working air, we have few things. So we need to perform transformation of pneumatic energy into mechanical energy of moving mass. So basically it's the cylinder. We have somewhere air, we push the piston, and then we have a moving something, or we perform the force, or we use it in the press application. This is one of the most standard applications of compressed air, right? Standard pneumatics. else we can use it? We can use it for blowing. So basically we use this pneumatic energy as the kinetic energy of the flow for cleaning or blowing application, for transport, a lot of things. Basically, it's also used in the chemical, in the cement production, in various things. So there we need the flow. And another thing is that we use those pneumatic energies, the kinetic energy of flow, to generate vacuum. From the technical reasons, it sounds a bit bizarre, but we have this application, and vacuum applications are widely used nowadays. And if we go back and think about the feeling, what actually creates the contributes to energy consumption, it's a volume and pressure, right? So we always have volume and the pressure. So here we have the volume, is the filling volume of the cylinder, of the tubes between cylinder valve. We have the volume to blow something, to clean, for example. We have the vacuum to create this vacuum there. And those are consumers. So the consumers are our actuators. It's our application of those pneumatic systems. So, but the question is, do we actually need technically those 6 bar at each consumer? Can we adapt it, and why it is matters? So now you see that there are practices that have been used like in the past, and well, now we don't have to apply the same practices for those tools where the certain torque is required. Here we need a certain force. And this magic number, it also matters on all levels and on all applications. So first of all, of course, it's important if we see the pressure level contributes to energy consumption, as well as pressure drops, filling of the geometry and the dead volumes. It all comes to the fact that we need to size correctly our components. And this is, for example, we can see on the example of the cylinder. And there are 3 steps how to choose cylinder, 3 standard steps. So first of all, the choice of the cylinder starts with the identification of required task parameters, right? So we have the machine, for example, a press machine. We have a pneumatic press there. We need to understand the force that we require for this application, the velocity. There are other, and positioning. There are other dynamic acceleration, maybe. There are few things that are important, but the most important is usually force and velocity. Then we calculate the required cylinder diameter under standard system pressure. And you see here on the right-hand side, I showed this is the catalog of the manufacturer, that from every manufacturer you can find it, and it's again standardized. You see this pressure for determining piston force, 6.3 bar. So it means that it was calculated and tested the manufacturer at this pressure. So it's again our magic number here. And then we need to go to the catalog of the supplier. And for example, if we chose for calculated cylinder diameter of 26 millimeters that would require for this task, then we need to choose cylinder 32 from our standard catalog, right? And since let's assume right now that we cannot reduce this pressure, that now the pressure is set standard because the supplier of the component told us that this calculation was done under 6.3 bar, and we cannot choose cylinder only under these circumstances, under these conditions. Let's see what about the consumption, how the consumption will change there. So first of all, here it's the comparison of cylinder with diameter 50 millimeters, 32, and 25 millimeters. If we again follow very simple calculation of the pressure and volume, you can see that the cylinder with a diameter of 32 millimeters consumes 41% less than cylinder of 50 millimeters. And this is a very common case in the standard pneumatics. In the standard pneumatic, the common case, of course, not the consumption, but in standard pneumatic is a very common case when we oversize cylinder. So, for example, we chose the 32, but then, okay, maybe we need to have more safety there, and the bigger the safer it is, probably or faster. But this is kind of gives feeling that it can save the application. And then we take the next standard cylinder from the shelf or from our catalog. And you see that only this safety, it already contributes a lot. And imagine you have in your machine not just one cylinder, but 50 cylinders, right? And your consumption of one machine is 40% more that's supposed to be. And you have not one machine, but 6 machines, and you have a compressor for those. You understand, of course, like the logic. We're increasing volume here, and we cannot decrease the pressure level here, because this is the standard thing. It always has been done like this, and this practice of this pressure level was adopted. So it means that to reduce energy consumption, we need to size correctly those cylinders. So we need to calculate, we need to not oversize it, and we always need to pay attention to this. And I want to show you now the standard cylinder sizing and this sizing dilemma, basically, right? So you see here the numbers that are standardized nowadays. So we have here, I didn't show the smaller one, but we have from 32 to 125. And then we have certain gap, 40, 50, 63, 80, 100, 125. And this, each of the piston force and the 6.3 bar contributes or creates the extracting force. So like we have retracting, extracting force, and this is usually the criteria how the machine designer, machine builder, or system supplier chooses the cylinder. As I said before, I calculated 49, I choose 50, okay? But look at this gap between the force. The gap is actually huge. So between 50 and 63 millimeters, it's 1,200 Newton. The next one is 1,900. Next one is 3,000. And another one is already 5,000. Another one is already 8,000. So, and here you see the consumption of this. This is the already energy cost calculated under the same condition, under the same pressure, number of cycles, and number of years, number of days how this machine works. So look at this. We have here difference between 1,400 euros of operational cost only for one cylinder and 2,300. 900 and almost 1,500. Higher we go in our force, bigger the gap is. And this is the problem. The problem is here, what if we need 2,000 Newton? If we need 2,000 Newton or even 1,000 Newton, we cannot do anything with the pressure level, and we choose 80 millimeter diameter with almost 3,000 Newton that contributes almost 40% more into the consumption. So there is a zero flexibility in these numbers. And the problem is that pneumatics, if you see that the standard pneumatics was actually not designed to be efficient, because this gap, it doesn't make sense. It doesn't make any technical sense. It should be opposite. It should be bigger gap in the smaller diameters and smaller gap in the bigger diameters, right? But where are those numbers coming from? In 1800, the French engineer Charles Renard created the Renard number system. So this is the geometric progression that was adopted by International Standardization Organization for various industries, including pneumatics. So it is you can find in electronics, you can find in chemistry, in many industries. It's a very good initiative, right? Because we need to have standardized sizing. We have to have standards to be able to communicate information to customers, to be able to optimize. I mean, it is essential and very important. However, it was also applied for the cylinder bore size. And if you just multiply the current bore size but by 1.259, you get the next cylinder size. So good news, you don't have to remember this anymore. What is the standard cylinder size? You simply just multiply it. But the system was adopted in 19th century. And of course, it helped and revolutionized the design and manufacturing of that time. However, I think nowadays for 21st century and for 2023, it's a little bit old, and we are under pressure of the energy efficient solutions. The question is how we can provide with energy efficient solutions when we still use this. We have this standard of the standard cylinders, and we cannot change it because it's already best practice. And I think that pneumatic system can be efficient, and I'm sure about this. It's not only my opinion, but opinion of various manufacturers and the system suppliers and also the machine builders, that there are nowadays slowly on the market are coming the best practice on the optimizing and reducing the consumption of the application. So once again, I remind you, and I will always remind you, always remember we have pressure and filling volumes. So we can reduce pressure level. Yes, we can reduce pressure level at the compressor, and we can size cylinder according to the pressure level that you have. It doesn't have to be 6.3 bar. As you could see, you could choose bigger cylinder under the lower pressure level. You can also reduce the pressure drops. It doesn't have to be half a bar or 1 bar. It's too much. And if you hear from manufacturers that pressure fluctuation of 1 bar is too much, is not right. So because physically you always have pressure drops, but not as high as this one. And of course, the filling volumes. So you can use correctly. You can size it correctly. You can reduce the flow. You can reduce, for example, also the dead volumes. So when we always play with these two things, we always need to find a balance for our functionality, for our application, and the pressure level, and also the flow. And here, just one of the things that this, for example, was developed by Artema organization. So I'm using the table from them about the various energy saving measures in the levels of the actuators, distribution valves, distribution line, and also filter regulators. On purpose here, as you see, I don't touch the compressor because we're not talking about the generation. We're talking about how the air is used. And well, my main idea is to show that the first we need to start from the application. So we need to reduce the consumption application and ask ourselves actually why I have this pressure level. Do I need this pressure level here? Do I need this cylinder actuator? Do I actually need this technology? Maybe it's not a pneumatic cylinder that has to be used there, but maybe it's an electric actuator. There are various factors that have to be considered. Today, I wouldn't like to go into the details about the cylinder sizing, but you can find those tutorials on our YouTube channel, because no boring pneumatics. So I hope you can have also some interesting insights about there and learn more things about new technologies that are already available on the market. And what I wanted also to tell you there is that there are various technologies that provide, for example, the cutting of the volume, the use of expansion energy of compressed air inside the cylinder. It can also reuse the energy. It can also reduce the pressure for the return stroke. So it's not only this odd sizing of Renard number available nowadays in the market. There are various technologies that can be nowadays implemented, and they work totally fine. Another thing that also is very important, it's that energy efficiency is also performance of your system. So what does it mean? It doesn't mean that it's always a balance. Either my system is faster and better or more energy efficient, or maybe it consumes more or it consumes less, but it loses in performance. In pneumatics, it doesn't work like this. Energy efficiency in pneumatics, in compressed air, it's always the result of correctly sized system. It's very simple. If your system is sized correctly, if there are no problems in the application sense that you have enough force in the cylinder, enough blowing force, enough speed, and there are no problems of the leaks inside the sealing of cylinder. I mean, I'm going now into the details, but this is a very important thing that we need to remember. It is always the result. And another thing I want to talk about, the third magic number, it's the pressure drop within the application. So it's considered that 1 bar pressure fluctuation, it's fine. And in my opinion, we need to reconsider this, but also in the opinion of physics and thermodynamics and real best practice that we see in the industrial sector, it's a very high pressure drop within the application, within the machine. And I would like to share with you a real use case to show you how actually considering and optimizing the application first is very important. So we start here not from the compressed air system itself. We start from the application. But let's see. We have here it's one use case of one of our clients, and you see the cost in the Moroccan dirham. So the company is in Morocco. And we got information from them about the consumption of their compressed air. They did a great job in the analysis of the compressed air system. That is essential and first step to start optimizing and reducing energy consumption. So we saw the total volume, total cost. However, there were also some operational risks, right? The company wanted to reduce consumption, but operators also said, listen, we want to reduce consumption, but wait, before we need to be sure that our system works fine. So there were some pressure drops, there were some pressure fluctuations. Pressure fluctuations is the not constant pressure drop in the application. And there were some leaks and so on. And of course, when we see in the closed box only compressed air system without the application, we make one conclusion. The conclusion was that we need to repair leaks, we need to redesign compressed air room, we need to buy more efficient compressor, we need to, I don't know, maybe compensate those pressure drops, right? It's no, not to have them, maybe we need like a big receiver. So the information that we got from the previous audit, and because I want to make it, because I think compressed air is fascinating, very interesting. I will use my magic tricks today in the slides that we asked our magic ball about the application. So what is actually application and how air is used? And what are the magic numbers of this application, why it causes such a high pressure drop, and what is this? So in this factory, the client replaced old technology by air knives. So basically, he uses the flow application, right? So before I showed you, we can have the cylinders, vacuum, flow application. So in this case, it was a flow application to clean the surface. So we did the model of the projected application, just application, because they changed it. And the most important thing for customer was what is the blow-in force and what is the consumption or the flow rate, cubic meter per hour. So this is basically the requirements, how the air is used. The air was used like this. It has to provide with the blow-in force of 120 Newton with a certain 700 cubic meter per hour. So we saw our model correlated with the technical standards. And there are some little flaws in this application because one pieces was changed, another one not changed, and so on and so on. So it was the pressure drop within the application, the pressure fluctuation 2.3 bar. Of course, it was not normal for the customer, was not satisfied. And if we calculate back, the required pressure of the compressor was 0.8 bar. So not the magic number of of 7. However, the system didn't work on this with this blowing force and with this pressure, because we saw on the manometer the flow was very low, and it was okay, but sometimes not okay. So we saw that it was not a real application. And if we calculate the real application and model this real application, we see that the required pressure, the outlet was 2.2 bar. The blowing force, actual blowing force during this operation was 70 Newton instead of the projected one. The consumption, of course, was lower. And the required pressure was 3 bar with a drop of 0.8 bar. So, and then the next step is, of course, to take this application. And after understanding what application does and what is actually process requires for this, we always need to take the full holistic picture and to put this application, inside this application, in the compressed air system and understand how everything works together, how everything correlates together. So the results were following that. It's true. The measurement confirmed that this is this was like the situation on the on those air knives, that the pressure was low and the flow rate was also lower than projected. The air cost more or less the same, and the pressure drop around 1.6, 1.8 bar. So the application model corresponded, but of course, customer wanted to have a more efficient component, more efficient application with a higher blowing force and also with the better performance of the system. And here comes this question, but was the compressed air system actually ready for this integration? Because in our head, we have the machine and we have the pipe, and somewhere we have the compressor in somewhere 2 kilometers away or 1 kilometer away from this room. And it looks like a very simple system that should work and should adapt into this application. However, it's not like this. So it's a very complex system with various components, with various things that should be considered. So if we take the projected application, that what customer wanted at the beginning with the high blowing force, and optimized application with the pressure fluctuation. For example, here, when we optimized application, pressure fluctuation was 0.2 bar, that is normal. So you see it's not 0.6 bar, 0.2 bar, it's normal. And the problem is that if we actually wanted to have this output, we had to have a huge compressor with a pressure higher than 12 bar, with the required flow rate also very high. And the conclusion was that the system was simply not designed for this. It was not designed for this because this new efficient component that consumes less and gives more required a higher mass flow rate. And this was causing the higher pressure drop in the full system. And if we go back in the logic of the changing something in our system, we can say that integrating new efficient applications is always good idea, is always good. So because in this case, it was the open piping was replaced by the nozzles. And of course, it has the, I mean, it's just good. It's engineering great nozzles that should work and should have the better performance. However, the system that already existed before was not able to operate with these conditions. So the system compatibility has to be checked always first. So optimize the compressed air system. And what I'm always telling, we need to optimize the compressed air system regarding the application and not the system itself. We don't fix compressed air system, but of course we need to fix it. It's the next step. But first we need to understand how it is used and optimize this application. So we're not creating compressed air system for the sake of compressed air system. We're creating it to be able to perform something, to operate, right? To have the forces at the end, to have the certain flows at the end for our application. We don't buy air, we buy the application. And this is very important. And here I just will not bother you with the numbers, but one just to tell you, there are various options to do this. For example, in this case, we can keep the same functionality that customer wanted with the reduced pressure fluctuation, and we require pressure level, tada, maybe it's a magic 6.2 bar, maybe it's really a magic number. So in this project, it was like this suggested. But the air costs were higher than it was before. In the second option, maybe we can reduce a little bit the functionality in sense that, well, you saw the cylinders are oversized, right? That sometimes we have 3,000 Newton maybe where we don't need it. So sometimes we should question supplier of the machine, do we need this force? Do we need this flow here at all to adapt our compressed air system there? So for example, if we reduce by 22% blowing force, we needed the lower pressure for air knife, and the system redesign was now 5.2 bar, and with compressed air cost that were lower. And here now it's another tricky question. So you see, we always need to dive deeper into the application and be annoying and understand why it is so, why I need this force. Because, for example, from our experience, the application could be adjusted for flow pressure or for blowing force or for a higher flow rate. So here is the tricky thing. We have various applications for compressed air, and you saw it. And there are two different applications for the flow, for the blowing applications. For example, in case of cleaning, we need high flow but low pressure, where we need to blow the large surfaces. And for the precise cleaning, there we need the high blowing force, high pressure, and low flow. And most of the time, what we see is that it's, it's a tricky thing to just comprehend in one, because we have a certain ways of applying compressed air. We have a compressor, 7 bar, 6.3 bar, and then it just serves for all the application. But if we go a little bit deeper and understand this, sometimes maybe we even don't need it. So maybe we don't need this high pressure at all, because we need, our application is different, our requirements are different, or the process team doesn't need this. So it's always very important to understand first how the air is used. And or maybe sometimes we don't even need compressed air. So there are various things. We always need to understand the life cycle cost analysis, the energy cost, the process, how our process will change there. And the option 3, for example, was, okay, let's leave it the way it is. We need to change there something, of course. I mean, behind these options, there are modifications of the system, right? We leave this blowing force like this, and we leave the energy cost very low now. So, but the option number 4, philosophical question, technical question, do we need at all this? Maybe we can use an alternative technology, like I put a small blower that provide the flow here. It doesn't create any force. It creates 2.5 bar for pressure, right? We don't need there any compressor there. So we remove the compressed air system at all, and we just put a small blower that works only for this application. And those kind of questions, we don't say that something is right or something is wrong. We cannot say right away, remove all compressed air and put electric drives, because it doesn't work like this. There are so many applications where pneumatics is way better than electrics. There are applications there where electrics is better than pneumatics. Better, not that it's shinier and fancier. Better is because we took the application, we considered the functionality of this dynamic functional characteristic, this already said. Energy cost, we consider the full life cycle cost with the maintenance, with the investment. We saw the amortization curve, and only after that we can make a decision, take a decision, which application I use there. And then after this, when we have several options and we understand that we can choose the most optimal application for this and not the one that shines in the catalog. Like, for example, here you see there are 4 options, and we first ask about question functionality, and after the functionality, we already go back and we adapt compressed air system. So we don't design first compressed air system and then we put inside this compressed air system applications that use it. We design application of this and then we adapt the system. Maybe it's 2 compressors, maybe it's 3 compressors, maybe it's 1 compressor, 1 booster. Who knows? We always need to understand what is our requirement. So questioning back the design, as I said, design or check your application first. So this is the thing that your system doesn't have to work at 6.3 bar unless it's tools. Component sizing, it doesn't have to be the standard ISO components, or maybe it is. It doesn't have to be the pressure level of 6 bar for those components, or maybe it is. It can be other efficient technology there, right? So it can be, as I said, the market is now full with various efficient technologies, or maybe you just adjust the pressure reducer for the return stroke of the cylinder. And your pressure drop doesn't have to be 1 bar. This is within the application. It can be 1 bar if you have a big system until the compressor. It doesn't have to be that way. There are physical conditions, so there are physical calculations based on the standards, based on the test that help you to calculate the pressure drop that should be theoretically in your system. Plus, of course, we have some safety factors and so on, but 0.2, 0.3 bar, it's a normal pressure drop within the pneumatic system, not 1 bar, not a fluctuation of half a bar. And then when you choose your application, then adjust your compressed air system to it. So, and what I also want to say, if there are energy managers, end users of this, so you drive the performance. You can go to your manufacturer of your system and say, listen, I want to optimize it, want to reduce the pressure level because it's very high for me, or I want to see if I can use like multi-level system pressure. I want to reduce the pressure drop. Reduce for me pressure drops. Show me what are the other efficient components you put here. Are you sure that you didn't oversize those cylinders? Those things that it comes from people that are from energy managers and maintenance managers. So you see the state of the art, how pneumatics is designed. It's not designed to be efficient. And I showed you today only 2 minutes about magic numbers that we think it's the best practice. One of the real number, magic number that makes technical and physical sense is the critical pressure level at the ideal nozzle, that is 0.528. That's it. Then we have the Reynolds number, then we have other numbers, but they are proven in the laboratory. They're proven with the, it's not just that someone said that it's a beautiful, 90, see, it's an amazing, beautiful number. Let's now everyone use it for all applications. And if we go a little bit now into the philosophical question, this is what I call the implementation uncertainty energy efficiency curve, right? We have various stakeholders in this game. We have the suppliers of pneumatic components that have already efficient technologies. We have also machine builders that are willing to reduce their energy consumption, make their machine better. And we have end users that, of course, are more than interested to have a better performance and also to have the lower energy consumption. And the full idea of my webinar today, of my speech, is not to blame someone that someone does wrong and say, you use this number from 19th century, it doesn't make any sense anymore, right? I mean, it's really ridiculous if you think about it. But it's best practice. It's something that we adopted. It's something that was developed in 60s, in 70s, and we never changed it. When we think about the energy efficiency of compressed air, we think about the leak detection. That is essential, and no one can say anything against. And we also think about the compressor, right? We think about the compressed air. We go into the compressor room. It's very logical. It doesn't mean that something is wrong there. Not at all. We always have to follow the best practice that's been working. But as you see, Today, some things, they don't work. But at the same time, there are solutions that are available. And I think that there are various challenges to implement these solutions. And higher energy efficiency of performance of pneumatic system is, and this is I saw in my personal practice and when I spoke also with my colleagues, higher this uncertainty of the implementation. We're not sure, right? Is it going to work? It's some fancy schmancy cylinder that reduces something but doesn't reduce. No, I want to feel safer and use the other one. So there are not so many standards on pneumatics nowadays. There are some very important, but there is no standard how to choose your cylinder, how to size it, how to choose the topology of your system. There are some white papers, best practices, but it's not standard way. In terms of policies, compressed air is considered as an old technology. Unfortunately, it's used everywhere. And now you see it gets a big hype, not only in the standard pneumatics, but in the direct carbon capture, where it also has to be designed efficiently and not use the same technologies that used nowadays. Or, for example, in the, air storage. But we still need to think how to use it there. And we have experts, we have expertise. We need some behavioral change, like be a little bit more open-minded about different applications and to have this information. And we need also the modeling tools. And today, I would like to invite you to AirG movement. So what is this? AirG movement, it's a very new thing. We're launching it in October. And you can sign in to this. It is a platform where we so AirG comes from AirG and energy. So we will have there the collaborative software for a efficient design of compressed air system. It's free of charge. You already can download it. You already can use it. It's powered by Direktin, where we developed it. But we realized that we need more personal touch there. We need people, and I meet so many brilliant experts, amazing technologies. Like people write me, look, I developed this thing and it saves 70%. And what we want to do there, we want to have a common space, not only for suppliers of efficient components and the experts, but also end users. Because when we go to end users, someone asked me, okay, we need optimize this, but can you also monitor this, or can you do this leak detection or some other thing? So there is a need, not only on the informative side of this, on the educational side, but I think there is need in the collaboration side. And we would like to invite you, all the experts and also people that use compressed air, or just curious about it, or maybe you know some other magic numbers. So what we're going to have there, besides the software, that you will have all the energy efficient components that are available on the market integrated inside the software. We will have the interviews, and we started already some interviews, recording them. We will have also the workshops, not only about compressed air. For example, our first workshop will be on the multiple benefits of the energy efficiency by Dr. Corman. So she will present an amazing method, actually amazing tool that helps people to take decisions on the energy efficiency projects. So there are going to be different things, workshops about the quality compressed air, Industry 4.0, calculations. I will do more the educational content on the how to do calculations, what is behind those calculations. And presentation opportunities. In presentation opportunities is basically if you have an interesting service that is saves energy, that is really good, and you would like to promote it, you would like to show it, we will also have there. So it's going to be groups for discussion. You can go now on the website and to see the structure of this. So we're going to fill it up, and in October we'll launch it officially with our event calendar, with our list of experts, and of course networking and collaboration. So every month we will have one chosen topic besides the workshop, where we just have an open space to talk. Digitalization, is it Industry 4.0? Is it just fancy word for pneumatics? Artificial intelligence, do we need artificial intelligence, or we just need intelligence? So let's say this is gonna be a nice, friendly space for everyone, and you're welcome there. So I think it's something we can create really interesting. And today I see that I have 45 people listening to this webinar, so it means that it's high welcome, and its topic is very interesting. We had 130 registered for that, and they will also get this information. It means that compressed air is a fascinating thing. And of course, there are, as I said before, there are also new applications of this that also would like to move from the soft robotics to the direct carbon capture, and to see how it can evolve. And there you can come and see new technologies and new opportunities. You can already sign in there. So I promise you, I'm not going to send you any spam. maximum once a month, it will be announcement of the event, of the things. You can contact me directly if you would like to, if you have ideas, because again, it's the collaborative space, right? We see what works. If groups works, discussion doesn't work, or you feel comfortable to be more on LinkedIn or things like this, we will see. I don't know, but if you have some ideas, suggestions, or you already want to be an expert with your profile there, and ready to organize a workshop or some event there, let me know. And well, this is my thing, and I see here some information about this very informative session. And yes, you can get a recorded video later, of course. You can DM me. You can DM me, and I can send you. Otherwise, I will forget. And amazing. Yes, someone wrote amazing. Thank you, Ahmed. And very interesting topic from Bernd. Worthwhile content. Thank you so much. So I hope you enjoyed it. And join also No Boring Pneumatic YouTube channel. So there I have more educational content and things. And please join our AirG movement. Next event we're planning in 2 weeks. We will discuss the comparison of pneumatics and electric, and we'll think if the electrification is really worth it, and when we should decide for the electric drive. Thank you very much. And yes, please connect to me. And yes, thank you very much. So thanks, Abate and Bernd and everyone. Great. Enjoy your day, and let's make pneumatics more conscious and more energy efficient. Thanks, everyone.